Okay, great. So, hi everybody, welcome back. The organizers very kindly offered for me to bump my notebook slightly into the last session. What I did is, in order to get it working again on Binder, I basically cut everything out of my online notebook. Things were kind of held up because basically a couple of my new lessons I put in, I hadn't built it for a while, and so this notebook hadn't changed, but my other notebooks were basically of a rather large size due to animations, and I tried to clear the kernel, but that wasn't working. So Binder was falling over basically because of the large size of the build, because of all the graphics and animations. So what I've done now is I've cleared all that out, and so hopefully it's working and it's built and it seems to be running. So what you can do is you can navigate to this rather long HTML. So it's under my https :// adriantompkins.github.io, and then it's climate-book, and then notebooks, and then part two underscore CDA. Sorry for the long, because I've split everything up into chapters now. Okay, and then CDA3 breakup. Okay, so when you type in that address, you will come out to, let me just move this over, sorry, like this, and minimize the window of the video. Okay, let me do this. It should open directly this static version that looks like this, CDA breakpoint analysis. Okay. And as I said, the book at the moment, I've just hacked it. It's only got 3 chapters, but because we're only using this one, it's fine. And then I'm going to reinstate it afterwards and try and sort out the memory issues for that. Okay. So if you open that in your browsers, okay, and then you'll see that these are buttons across the top because this is just a static page. Okay. So if you look at this little rocket ship, it opens you the possibility of actually launching this in Colab or Binder. Okay. And so if you click on the binder option, it's already compiled. It should be cached. I haven't touched anything or pushed since I last built it. So I'm hoping it will work for all of you. And it should open then the binder interactive version here, which is under this like hub.2i2c mybinder.org. Okay. Now, it may be that for some of you, Binder does have a little bit of a limit, and you might find that the server is basically not available straight away because there's a lot of you in the room all hitting it at the same time. So I'll just give you a couple of minutes to open that before I start going through it. And then maybe somebody in the room with a microphone can just kind of monitor how the progress is, maybe ask around, get people to show hands when if they're having problems opening it. So let me just give you a couple of minutes to open that there using this.
Okay, sounds good.
Okay, sorry, it's super difficult trying to do these things remotely, also with the lecturing. I've never been a big fan of the not been I like to bounce off my audience. So, oh, by the way, while you're doing that, I had a quick chat with Simona, and she did confirm that my intuition was correct about the correlation map. The second question this morning, and it is basically the dynamics. The correlation is high where the main import of moisture is occurring at low levels, so you have the highest correlation in those locations, both in the west and the kind of northeast of India. So the answer I gave this morning from intuition was actually the right one, it seems. And again, I apologize for not being more on the game regarding that. I was perhaps a little
Thanks, Adrian.
uncommon. Yeah.
Yeah, I was the one who asked, so thanks.
Yes. Okay. Yeah. So she said, yes, you were right. It's not the storage. It's basically the dynamical picture of where the main, the general moisture flux. They are the two main areas where it's occurring within the monsoon season. So it reflects in high correlations in those areas. Okay. I just thought I would follow up there because I had a quick chat with Simone this morning about it.
Okay, so maybe a quick show of hands if you are able to do what Adrian said. Or if you're stuck, can you point out, can you raise your hand?
When I tried it last year, I found that because of, maybe 50, 60 people hitting the same thing at the same time, some people had to wait a few minutes before they were able to get the server to launch. I don't see the room, so it's difficult for me to know. It's just to kind of know how things are going. Let me just minimize that again. One second, let me minimize this. Because I have one of the things you can do is you can actually, how do you say, let me close down this as well. You can actually basically, what was I going to say? You can also clone the library directly from GitHub if you prefer, but then you need to set up the environment. Okay, are people ready?
I think so. You can move on. There's some
Okay,
issues,
good.
but I can handle them maybe.
Okay. If you find somebody, but some people have managed to launch it and have this open, yes?
Yeah.
Okay, good. So if you can pair up with somebody that's not working, and then just be a little bit patient, and it will open eventually. It's just there are some server limitations on the free version of Binder. So all I'm going to do is this is just a notebook I wrote that kind of basically goes through this segmentation analysis and then applies it to the Monsoon. So I'm not going to go through this because I talked about this morning. We do the segmentation, the cost function, and optimization. Okay. So basically, what we're going to do is, and again, in order to make this quick, I'm not going to go through the code line by line. I'm going to invite you to mostly use the time after this session if you're interested to follow up and go through a little bit more carefully. So first of all I do in the first case, before we even start the Monsoon, I just want to show the segmentation super quickly. So we just make up some data, which is just like basically a linear relationship between our xi points with an offset c and then some random noise. Okay. So this is all that this routine does. We send arguments of basically where we want the split to be in the series, and then we have a slope and intercept for the two parts. So if we run this and give this a try, and then we say, okay, let's put the split point at 50. I've got two sets of lines, and as I put here, I've put a default of 8 in here, and you can challenge the algorithm afterwards as an exercise by setting this to other values, and then I've got a value of noise. So here, just to make things really clear, I've got a very small value of noise, and if I run this, I get a data like this, which basically has a very clear break at our chosen point of 40, okay? And as I said, later on in the exercises, if you want to play with this, you can change the slope and the intercepts, you can increase the value of the noise and basically try and challenge the algorithm. So I'm starting off with a really, really easy example here. So that's all we've done in these two kind of routines. We've just set up two linear points, and I'm just showing the kind of true line of the fit. Okay. Why are we doing this? Well, basically, whenever, like, just, especially for you, those of you just starting out in your careers and so on, it's the same with my diploma students here. It's always best when you're starting an algorithm not to immediately jump into a real life example, but to test it out in a very simple case where you know the answer. And that enables you basically to test your algorithm in a kind of controlled environment and make sure that you're not doing anything silly or having bugs in it and so on. Okay. And then basically, in order to do the fit, we have like three things we need to do. So what we're going to do is, first of all, given an input data set, we're going to just split it up at an arbitrary point and turn it into like basically two segments. Then we have a routine piecewise polyfit that just basically fits the best linear regression lines to the two portions. And I just make a note here, by the way, here we're just using very simple linear fits, but you can use this code to actually do higher order fits if you want to, like polynomials and so on. Okay. And then to find the change point, we're just going to cycle. We're not using any clever algorithm because it's just a time series. We can just use a brute force approach to kind of basically cycle through each of the possible splits and find out which one minimizes the root mean squared error. So basically, this is what the next thing does. You can see the split just returns the time series split at point n into two parts, okay? And that, I don't know what's going on here. Let me try and just reload. I'm going to make this wider now. Let's try this again. don't know why it was just jumping to the end there. That was very bizarre. Okay. Okay, now it's working. Okay. So split, and then this is the second part of the routine, which essentially just fits basically it calls the split to split the X and the Y up, and then it just uses this NumPy routine polyfit to do basically a fit when by default order is just set to 1 for a linear fit. Okay. And then we basically calculate basically the sum of the squared errors. So here we're using the sum. We could also apply the square root to have the root mean squared error, which I mentioned this morning, but it doesn't matter. We can just minimize the sum of the squares. So we just take y minus y predicted line and return that root mean squared error. So if we run this, and now we're going to try and actually just show the fit. So first of all we're doing in the next cell is we say, okay, let's take a guess at 40, which just so happens to be the right split, right? So when we run this, lo and behold, the green line, which I just plot over the top, and you can see it lies straight on top of the red and the blue, which is the true fit. Okay, so that's not exactly surprising because we knew exactly where the split was. So you can see that the green line fits very nicely, and the squared error score basically between the fit and the data comes out at basically 25, and this is unitless, so there's no units here, okay, because it's just a arbitrary value on the y-axis. Okay, great. But of course, in reality, when we get a data series, we don't know where the split is going to be, okay? So we knew the answer, but what about if we basically take a wild guess, and so we just say 50 this time. So you could have just basically edited n here. I've duplicated the code because I do have a bit of a bad habit of playing with these things in front of my students and then forgetting to change them back. And so then next time I open the notebook, the text doesn't really match up with what's in the boxes, which is what I found yesterday. And so that's why I repushed the book, which then of course messed everything up this morning, sorry. And I just noticed I had 70 instead of 50. So I thought, oh, I just quickly change that and push it. And then everything fell apart and stopped working like about 50 minutes before I was about to talk. So maximum panic mode this morning. I was like, oh no, what did I do that for? So now we're going to take a bad guess. And all of you there working with your binder, okay, I'm trying to do this quickly. Normally I do this a lot more slowly, but do whatever you like. Go to town on this and try different splits. So if I try 50, it looks like this. Okay. So the second part of the fit, of course, is still looking really beautiful because we've just cut down part of that linear line. But the first part now, because these data points, we're trying to split at point 50, we've got these points, but also these points in the linear fit. So these points here are pulling the line down, as you can see. And so they've made the error about 10 times larger, if I remember. See here we have the RSS score now is 200, whereas before we had 25, okay? So it's about 9 times larger. So you can see immediately, if we were to compare those two cases, we would much rather choose our split at 40 than 50 simply because the error is much lower, okay? So hopefully that's clear so far what we're doing. Everyone kind of like nod and if it's so far clear. How are we doing, by the way, of people following? If you have a show of hands in terms of following it interactively, do we have like 80, 90% of the people with it running now?
It seems so.
Seems so. Okay, good. Thanks. It's very worrying. So I feel so cut off from you. It's not just the food I'm missing. It's like being in the room with you all and having fun on this. But there we go. Anyway, so now we're going to do the minimization, okay? So it seems that we've got the concept, woohoo, okay? So now all we're going to do is I'm not going to try anything fancy. We're just going to simply cycle through all the points, okay? If we had a huge data set, then maybe you'd want to do some kind of like, how they call it, slice and divide kind of algorithms, which are more efficient. There are actually packages that do this, should we say, process directly and probably more efficient than this. So in this case here, though, I've kept to the manually coded up version. Okay. So this was actually based on the code that was used in the original paper, by the way, this change point analysis. So all we're doing here is we take in the X and Y values and we simply loop over our break list, sorry, our break list of potential breakpoints. Okay. And then we simply here find where we minimize the error. So we look using this nan-arg-min function. We just have a whole vector, basically a list of RSS values, so which we've just created here by appending, and then we just basically say, okay, that's where we basically find the breakpoint where we minimize this root mean squared error. So if we try it out now, okay, so we loop over, and hey, presto, of course, in this case, we have an example where the noise is very small, the breakpoint is extremely clear, and we end up with the breakpoint being found exactly at 40. Okay. So because I'm not in the room, it's difficult for me to kind of break out and say, okay, now try and see how people are going. So probably what I'm going to do is go through this fairly quickly, but I invite you to go back and challenge this algorithm. So make the noise larger, run it again, basically change the intercept and slope value. So I gave an example that if you change that value of 8 to a value of 15 in the offset of the second segment, it makes the lines almost join up. So only the slope changes, okay? So you can try that and you'll see that it seems to be pretty robust, okay? So we can plot then basically the output, and then this is the basically the true breakpoint and the one it's found. So because this is a really easy example, then it just fits it spot on. What you should find when you're playing with the data is if you increase the noise or you bring these points closer together, then it becomes a little bit less certain. So maybe instead of picking out 0.40, it starts to pick out 38 or 43. So it's still usually always in the ballpark, but the noise can make this a little bit basically uncertain. Okay. So one of the things I've added, because I actually gave this example in the last school last year, and at the time we just kind of went sailing on merrily ahead. But one of the things I've added in the meantime is I've now actually go through the Davis test for breakpoint significance, because this process will always find a breakpoint, okay, even if I gave just one single linear line with no breakpoint at all, with noise on, of course, this will still give us a breakpoint, okay? So I don't want to go through the details now, but you can read through this afterwards. So what this basically does is this test says, okay, we've got this basically root mean squared error, but how does that compare to our null hypothesis, which is basically there isn't a breakpoint in the data, okay? And so this statistical test basically sets up a T statistic, which is the log of the single fit ratio to the piecewise two segment fit, okay? And so there's a little bit of text there about how we set the number of degrees of freedom, which surprisingly is not related to the number of points because it's actually just related to the number of fit parameters in this case. So it's a little bit different to, for example, when you want to test the significance of a correlation. And so I'm not going to go through this in detail, but if you're interested, you have that there for reference. And so I coded this up here in this Davis test. So this is, for those of you that saw this last year, this is something that's new in this, which just returns the p-value according to this test of basically the single versus two basically fits. So in this case here, of course, because this is super, super easy, then we end up with basically a really tiny p-value, and this is, of course, highly significant at this tiny, tiny p-value. So what you can do is when you're playing with this, so this is my ideas here. So if you challenge the algorithm, you'll see that it starts to get uncertain in exactly timing where the breakpoint is occurring, okay? And then you'll notice that in some cases, then even if you make it too close together, for example, if you slowly change it and make the slopes more and more similar, you'll find that then your significance test actually starts to fail, okay? So I'm going to carry on then onto the Monsoon onset example, but again, I invite you to just play and understand how the breakpoint basically algorithm is working. So I gave my quick introduction this morning, so I can move quickly through this. Of course, I've left it inside the notebook because normally I work just directly from here. So this was the rainfall, just to remind ourselves this morning, and it was kind of interesting to see just how uncertain your assessment of the onset was. Again, it kind of highlighted how when you try and have thresholds based on noisy processes and so on, or even like accumulated rainfall amounts, you can basically lead to quite a lot of uncertainty. Okay. Again, I'm not going to break out here because I'm not in the room, and so it's hard to kind of thing. It would be nice, of course, kind of looking at basically some of these issues. Again, this is kind of what we did with the Mentimeter this morning. So, like, where would you define the onset? What are the difficulties? And have an open discussion, basically, of the difficulties of having threshold onset parameters. It's the same thing, by the way, with the African monsoon. When you read through some of the onsets, there's really, some papers will have onset parameters which are maybe specifically targeted at certain fields, so maybe they're interested in the onset from an agricultural point of perspective, and then you get some very complicated sets of rules that basically define onsets. It has to rain a certain amount over a 3-day period, or maybe 3 days in consecutively. It can't be followed by a break of more than, say, 7 days. And so you have a lot of these kind of if then else conditions to say has it onset or not, which can be quite subject to being very sensitive to small perturbations, as I said, in rainfall amounts. Okay. So I went through this morning, so I'm not going to go through it again because we already heard this. Basically, we were building up this index based on the water budget, okay, and then we talked about this slide this morning that basically showed these various components, okay, and we had this discussion within the talk about the key features of precipitation, evaporation, and the seasonal cycle of storage. Now we saw that basically the moisture flux convergence over the continent traced fairly well the P minus E, and that storage was a relatively minor component of this budget. Okay, so there's some text there that basically talks about this here. Okay, so what we're going to do now is just basically sucking these packages. Sorry, I'm scrolling forward. Let me just come up to date. And so now, bam. Okay, so we're just basically using, I've imported NumPy again, although I think that's a double import actually, matplotlib, because I added all the stuff earlier on, so I do need to update this a little bit. And I also have this quite generalized, so this is for India. The next couple of cells, ignore it. You can, I've set it up so you could in the past, although they've changed it, actually import the how do you say, the data from the climate data store. But since the update of the data store about a year and a half ago, a year and a quarter, it's really, really slow. So you can't do that in class. So what I've done here, this basically does do nothing. And I've put the data pre-processed on our ClimaDogs disk, which we'll read remotely. Okay, I've just done that because otherwise it's just no possibility of doing this in a short class. Okay, so we're using this prepared data online and we're picking up here. One time this morning, because I think the binder was struggling a little bit, I did have an issue where the access to the data fell over because of the I think again the speed problem. I just reran this cell and then it worked fine the second time. Okay, so if you have a problem later on when it starts to read the data in, just rerun these cells. I think it's just to basically again the connection timing out. Okay, so all I do here is I get a list of the data files. Okay, and then these are the field names. So these are just the field names as they're stored from the era 5. As I said, I do everything here in era 5. So TP is total precipitation, E is evaporation, and the VMID is just basically the vertically integrated moisture divergence. Okay, and then so I just have some sign changes to get everything in the right sign. Okay, and then these are how we're going to actually call it. I could actually put this into a dictionary. I should get around to making that a little bit nicer. Sorry. I wrote this when my Python was even more basic than it is now. So I've gone from a 0 level Python writer to like a level one maybe, but still pretty basic. So here we're just going to loop over the data and get the data. So this will take a little bit of time just to load it because it's reading it over the net. Okay. So it goes to start and it should move on. It might be a little bit slower in India, but it did work okay last year as well. Okay. And I just hope we don't get any denial of service. There is an amazing, just because we're talking about monsoons and convection, you see me looking out the window, but I don't know if you can see this on the camera. Oh, this storm just coming in now. Look at this uplift from the
Background.
stuff. Can you see that?
Your background is blurred, so maybe you
Oh
can.
no, okay. I need to turn that off then. Oh, it's just so beautiful. Why everyone's running this because it's running slowly. Can you also canvas people to see how the basically things are moving ahead in terms of the let me go back to the Zoom. Where's my thing gone? Zoom, here we go. Oh, I have no idea. Oh, here it is. It's over here. Let me go back to here. Need to get my meeting controls back. Oh, there they are. Sorry, I just have to show you this. Blur my background off. Okay, now you'll see all the mess in my office. It's a bit embarrassing, but this will compensate for it. Do you see it now?
Yeah.
Pretty spectacular, no? Sorry, I know it's a bit of a side thing, but it was really distracting me. Yesterday we had the most amazing storm. It's incredible. We only normally get those in July and August, and I will forward to the organizers the time lapse that we were taking of this thing yesterday. It was incredible. We had for a May storm, it was pretty incredible. 30 millimeters at the two gauges in something like 45 minutes, which for a May shower is pretty spectacular. Anyway, sorry, I digress. Let me go back and hide my meeting controls again. Hide floating meeting controls. Because everybody in the audience is probably just as addicted to convection as me. So these things are really distracting when they're coming in. That's why I kept looking up. Sorry. So where am I? Okay. Can you just see if everybody managed to run this cell and it kind of completed okay? We'll do a canvas of show of hands just before I move on, because that's the one dodgy cell that sometimes falls over.
Could you load the data? Yeah, I see a few thumbs up. So
Okay, good. So if that cell basically went okay, then this is just like plot year D-list, and it just basically makes a plot of these three different parameters. So you'll recognize this straight away. So this is the era 5 data we've read in, okay? And you'll see the general basically moisture flux convergence, the rainfall in the thick dotted line, and then the thin line at the back, which is the evaporation, okay, in millimeters per day on the left axis and day of year at the bottom. So if you remember the plot I showed from the Walker and Baldoni paper earlier from 2016, you'll notice all the features are there roughly similar. So even though we're using era 5 rainfall, which of course is not necessarily the best because it's a moist process, but nevertheless, we can see the large scale features are well produced in era 5. So that's kind of a sanity check there. Okay. Normally, I would get you to think about what are the issues with reanalysis, in particular the lack of a closed moisture budget there. But we can see that the non-closure is not so tragic that it messes up the large scale picture there. Okay. And so then what we're going to do now is there's another, basically, we could have just accumulated it within Python itself, but I'd already processed it with CDO offline, so I'm just going to read that in as well. Okay. And so if we basically read this in as well, so that takes a little bit of time, but it's only one field, so it should be a little bit faster. Okay. And then we're going to make a plot of this with the cumulus mass flux. So we've just read in the cumulus. I'm just obsessed with cumulus. The cumulative, basically moisture flux divergence, which has got its own little legend over here now, but it's added after the plot. And here we go again. And you can even see, if we look at this, we've got those two little bumps, but it's a little bit different from the GPCP. Remember this morning GPCP, those two small bumps around the kind of this general zone were kind of equal, whereas now we have a more of a broader minimum here and then a slight bump down just afterwards. But the same argument holds that, if this bump was slightly deeper and we were just taking the bare minimum, we would jump across to here, okay? So now we simply basically want to do our fit. So we have our piecewise polyfit, okay? And so what we're going to do is, this is not finding the bare minimum. This is basically just taking an arbitrary guess. So if you notice, this is not the piece of code which actually goes through, cycles through and finds the actual breakpoint. It's just using the first part of the code. It just does a polyfit at an arbitrary kind of breakpoint. So what I'm doing here is I'm just saying, okay, let's guess at day 140, which is about here, okay? So it's kind of in the ballpark, but it's a little bit later than this minimum, okay? And so we chuck all the data in, we take a guess, let's take a plot, and then this is what happens. And it's like, uh-oh, this is not looking good at all, no? So this green line kind of does a reasonable fit to the first period, but look what's happening over here on the right-hand side, okay? We've got this really bad fit. So why is that happening? So why do we have such a bad fit here? I'd like to hand the mic around and ask somebody in the audience to shout out, but maybe someone can shout out and you can repeat the answer. Why are we having such a problem with this last part of the fit? Anyone have any ideas what we're doing wrong? It's something I mentioned this morning.
We're picking up the demise as well.
Yeah, exactly. So we're taking the whole series, we're breaking it here, but we've forgotten to kind of cut this bit off the end. Remember in Simona's work, she was kind of cutting off at day 250, you know? So we want to basically throw away that last portion there because it's kind of giving us a little bit of a headache, you know? We could have also tried to do a 3-segment fit, okay? So that would be an alternative as well. Okay, sorry, just show you one more time. Look at this. It's dramatic, no? Okay, I'm going to have to turn my laptop around and look the other way because it keeps disturbing me. So what we're going to do now is we basically want to kind of chop off. So I've got this cut off, and all we're doing here is I'm just cutting the series off. You see, x from 0 to cut off, and the basically the cumulative moisture flux convergence. We're also just cutting it off there. So let's do that. And now things are looking a lot better, much more similar to basically the analysis this morning. But of course, because we're off from where the minimum is, you know, this last part here, that's looking pretty good, okay? But because we've taken a kind of pot shot guess, you can see that because we've got a lot of this curvature in here, it's okay, but we can probably do better. So what are we going to do now is we're going to let the algorithm basically cycle over and find the minimum. Now, that was our kind of rough guess, and we did okay, but yeah, 140 wasn't great. So let's just loop over. And where did it pick? It picked around day 125. So let's see what that looks like. And so if we basically do that, now we have this fit. And so if you look by eye, you can already see that the first segment is quite a lot closer. We minimize, and this is our onset that we've chosen here. So I've just plotted a vertical line over it. And you can see that, in fact, it's not the absolute minimum because we have those two minima, and it's kind of, you know, in the end, it's chosen something kind of in the middle. So it's not really the minimum of the function at all. Okay. And as I mentioned this morning, because it's taken into account all of the points, then it's much more robust. Okay. So that's why I wanted to talk about it there. Okay. So that's basically the overview of how we apply this this minimization to find the onset date in this notebook. Okay. And so basically, I've got a whole set of exercises here and a few clues at the end, okay, which you can work through. Now, I know you're supposed to discuss your projects now, so I think probably I'll leave it to the organizers locally, whether they, you know, if you want to do this afterwards or as a session, and some of you might even want to have a project, you know, based around this as well. So all we've done is look at the year 2000, okay? So one of the first things you could do is simply choose other years. I think I pre-processed through to almost 2020, and it goes back a few years before that. But you can just open up that Climadots web location in a browser and see exactly what data is available there. Okay. Or you can also go directly to the source, the CDS, if you have more time, if you want to do that offline. So you can use that little snippet of code and hopefully that will still work. Okay. So you could, first thing to do with this is you can run through this code because there are other years and you could look at other, just pick out different years, just change the year where it says year equals 2000 to 2015, 2016, 2017, and just look at the nature of each of the years in terms of the precipitation patterns, the moisture flux convergence over the region and where the onset is. Okay, so basically you can look through those years and then, you can say, are there years that are particularly delayed or particularly advanced? Okay. And some of you've probably already heard this week about some of the teleconnections with the IOD and also the ENSO in terms of early or late onsets and patterns of SST. So you can see, first of all, just from this very simple analysis, does the early or late onset agree with what you know from some of the other lectures you've heard this week. Okay. You could then actually loop over all the years and try and recreate a simple plot of the onset variability. Okay, so you've basically seen a plot this morning in the talk that I showed that had a time series of onset dates. So you can basically try to do that. You were having another class earlier, I think, which was basically an onset based on precipitation and local metrics. So you can actually see if you can actually compare this to the work you were doing earlier. And then you can also modify the code and snip off the beginning and try and focus on the cessation dates and also calculate the length of the monsoon. Okay. And then eventually, for example, some of you might actually want to download like P and E and actually look at, for example, the onset in seasonal forecasts. So if you were doing a longer project during the 2 weeks, you might be able to use this code and just adapt it to read in P and E from the seasonal forecast. And what you might want to do also with ERA 5 reanalysis is here we've just used the cumulative moisture flux convergence. So you could also just do the cumulative P minus E, which basically says, okay, we're just completely ignoring storage and assuming that these two are basically the same. And so you can see how that changes. So if you go through the code and modify it, so rather than doing this breakpoint analysis on the cumulative moisture flux convergence, you just do it on the cumulative P minus E, and you can make a second time series plot and see how well they correlate and how much things change by ignoring the storage in this way. Okay, or you can make either 2 time series or a scatter plot and so on. Okay, so that's something I mentioned down here as a potential forecast. I also mentioned CMIP, but I think in this length of workshop that's more difficult unless you have the data already available offline, at least for precipitation evaporation, you could do that. So I'm going to stop there and yeah, basically if there are any questions about the notebook or anyone had any problems, you can raise them now or you can raise them with me offline. I kind of rushed through it quite quickly because of the time restraint, but hopefully that was clear.
Thanks, Adrian. Let's thank Adrian once. So if you have any questions regarding the notebook, you can ask Adrian now.
Adrian, what's the status of the cloud now?
Of the what, sorry?
The cloud that you were looking through your window.
Oh, right, that cloud. Do you want to see it? Just moving off. There it is. I will forward to, I've got Mick's WhatsApp. I'm going to forward her the time lapse. Then she can maybe show it later in the week of the one that came through yesterday. Because, of course, you're right in your very hot period right now. So I'm sure it's a little bit toasty there. And so you can see how the weather here contrasts at the moment. It was pretty wild. I'll do that, Mick, in a moment. So you can, for a bit of fun later on, you can just pop it up on the screen. Okay, I'm going to stop sharing. Anyway, I hope that's kind of useful to look through, and you have the data there for the precipitation and so on, which is kind of already there from the ERA 5. It might also help for some of the other projects and so on. Yeah, I do invite you to kind of like play with the data offline. Let me just stop sharing. Yeah. And yeah, okay.
There are no questions regarding the notebook.
Okay, I don't know if that's good or bad. It either means everyone was getting it working or that it just wasn't working at all and it was a disaster. It's like one of the two.
I think it seemed to have worked for a couple of people at least. So
Okay,
yeah.
can I just see, now I can see the audience. Can people raise their hands who didn't manage to get it to work? That binder was just like not playing with you and it wasn't working at all. Can you raise your hand if it didn't work? Okay, can you raise your hand if it did work? Okay, wow, that's super. Okay. I'll also put I will reconstitute the build and I will pass through the link to my book, which was inspired by Brian Rose's book, but mine's a bit more of a hot potch because I use it for different lectures and so on. But there's a whole section. This is one chapter of a 10 chapter thing on just basic analysis techniques. So there's like Fourier, 2D Fourier, wavelets, EOFs, and so on and so forth. So if it's useful for anyone just in their studies, you'll be able to clone the book and have a little look through or look at the online version. It's just that I had to chop it all off in order to get this working with Binder this morning because it was just too big, as I mentioned. Cool. Okay. Thanks
Sounds
very
good.
much.
Let's thank Adrian again.
Thanks.